Okay, let's do it. Matrix multiplication. Start with that. So, you know how to multiply matrices, probably. You can take like two 2x2 matrices and multiply them together by doing rows times columns. So you do like first row times first column as a dot product to give you the first entry of the product matrix. So you would get, for the first entry, 1 times 5 plus 2 times 7. And then for the next entry, you would do 1 times 2 plus 6 times 8. So it would be 1 times 6 plus 2 times 8, the next entry. And then, you would keep going. You would move down to the next row, 3 times 5 plus 4 times 7, and then 3 times 6 plus 4 times 8. So the product of those two matrices ends up being I should have picked easier numbers, something like that. But obviously you can't multiply just any two random matrices together, right? There's a restriction on what dimensions the matrices can have. So like if you have this matrix, you can't multiply these two together. That doesn't work. So this is a 2x2 matrix. This is a 3x2 matrix. So the rule is that the inner dimensions have to line up. They have to be the same. So the number of columns of the first matrix has to be the same as the number of rows of the second matrix. So in general, you can do, if A is an m by n matrix, you can multiply it by some n by p matrix. And then the product is an m by p matrix. So these dimensions give you the dimensions of the product. Then the inner dimensions have to be equal to each other. So that's how matrix multiplication works. But so there's some like nice properties about matrix multiplication. If you take this matrix, it's diagonal, ABC, and you multiply it by some other matrix, just some random matrix. When you multiply these together, the effect is that the first row will be multiplied by A, this first entry. So you would get A, and then 2A, and then 3A. And the second row will be multiplied by this entry. So 2B, 3B, 4B. And then the third row will be multiplied by that entry. 3C, 4C, 5C. So some nice things about matrix multiplication. Another thing would be like if you have a row of zeros, then obviously when you multiply these two together, since you're multiplying the last row, since whenever you're multiplying this by the columns here, you're just getting zeros. In the end, your third row will have zeros. So rows of zeros sort of carry over like that. And sometimes we want only a particular entry of a product of the two matrices. We don't care about the whole product, A times B. We don't care about every entry. We only care about one particular entry or one particular row or column. In order to find that, there's some rules you can use. The ij entry, say the ij, so the row I, column j entry of the product A times B is, you can denote it like this, ABIJ. it's row I of A dot product with column J of B. So for example, if your matrix A, let's do like a 2 by 2. If your matrix A and B are those, you can, so let's say we want to know like what's the 1, 2 entry of AB. We can get that by just doing row 1 of A, which is 1, 2, dot product with column 2 of B, which is negative 1, 2. So that would be negative 1 plus 4, which is 3. So that would be the 1, 2 entry of A times B. And sometimes on the homework they'll say calculate this particular entry without doing any other computations. That's how they want you to do it. If you want a whole row, let's say you want the ith row of AB, then that's the ith row of A as a vector times B. So you're doing a row vector times the whole matrix B. So this would be like a 1 by 3 vector, and B would be like some 3 by 3 matrix maybe. And so your product would be a 1 by 3 row vector. And similarly, you could find the jth row or the jth column. The jth column of A times B is A times the jth column of B. So you're doing the whole matrix A, which is like a 3 by 3 times the column vector, which is like a 3 by 1, and you're getting a 3 by 1. 3 by 1 vector. So for example, if you take A to B, this matrix, and B to B, so A is a 3 by 3, B, let's say it's this matrix, this 3 by 2. We can multiply A and B together, and say we want to find the second row of A times B. So the second row of A, B would be the second row of A, which is 1, 2, 1, times B. So when you multiply these two together, you would get, let's see, so this is a 1 by 3 and this is a 3 by 2. So the resulting vector should be a 1 by 2. So it looks like you'll get 2 plus 4 plus 1, 7, and 1 plus 4 plus 3, like 8. So that would be the second row of AB. And then maybe the first column of AB would be A times the first column of B, which is 2, 2, 1. So that would be the product 1, negative 2, 0 times 1, 2, 1 times 0, 3, 3 times 2, 2, 1. So the product you would get is 0, 8. Sorry, that's 7. And that first entry should be -2. Okay. So that's pretty simple stuff. Let me check something. Stop that.
Those are only if the matrix is defined, right? So even
Yes.
if you could take the dot product of a row and column if the matrix is undefined, then that dot product is still.
Right. If you can't even multiply the matrices together in the first place, then you can't find any of the entries or anything. Okay, inverse matrices. So the inverse of a matrix A, let's say is another matrix. It's the matrix denoted by A to the -1, such that when you multiply A by A inverse, it's the same as multiplying by A inverse and then A. But you get the identity matrix when you do that product. Where this is like the matrix, the identity matrix has like 1s on the diagonal, 0s everywhere else. So, for example, the inverse of this diagonal matrix ABC, well, this matrix A multiplies the first row by A, second row by B, third row by C, so the inverse matrix should undo that operation and it should divide by A, B, and C across each row. So that means that A inverse should be the matrix 1 over A, 1 over B, 1 over C, and 0s everywhere else. So obviously this is assuming A, B, and C are not 0. So you can check that when you multiply these two matrices together, you get the identity matrix, so those are inverses. And then previously we talked about elementary matrices, which is a matrix like the identity but with one entry changed. So it's the identity except for that 2 there. The inverse of this elementary matrix is just the same thing but with the -2 instead of a +2. Because E inverse represents the row operation row 2 minus 2 row 1, and E represents the row operation row 2 plus 2 row 1, so those are like inverse row operations. They should cancel each other out. So in general, if you have an elementary matrix, the inverse just takes the one entry that's different and changes the sign. So an important thing is that not all matrices have inverses. Just like how calculus, not all functions have inverse functions. Same thing here, not all matrices have inverse matrices. So for example, the matrix A, let's say this matrix. So why does this matrix not have an inverse? Well, if you suppose A inverse is the matrix A, B, C, D, then when I say that these are inverses, I mean that A times A inverse will give me the identity matrix. So that means that 1, 0, 0, 0 times A, B, C, D should give you the identity matrix. But when you multiply these together, on the left-hand side, you'll get AB 0, 0. And that can't be equal to the identity matrix because this entry is 0 and that entry is a 1, and 1 is not 0. So those matrices cannot be inverses, which means A doesn't have an inverse. So not all matrices have inverses. If your matrix does have an inverse, then it's called invertible. It's called an invertible matrix. And if your matrix doesn't have an inverse, sometimes they call it a singular matrix. So if it's not invertible, it's called singular. So on the first homework, you did a problem where you solved the system AX equals B with an arbitrary vector B1, B2, B3 by writing it as A inverse, by writing the solution X as A inverse B, by solving for the X's in terms of the B's. And so in that way, you found the inverse matrix A. But now there's like more efficient ways to go about it, to go about solving for the inverse matrix. So the way we do that is using Gauss-Jordan. And so what you do is you take your matrix A, you augment it with the identity matrix. So for example, let's say your matrix A is 1, 2, 2, 6, and then let's augment it with the identity matrix on the other side. You want to reduce the left-hand side, you want to reduce A into the identity matrix, and then whatever operations you did, you do that same thing to the other side, and the other side turns into the inverse. So you want to reduce the left-hand side to the identity, and then the right-hand side will turn into the inverse. And that's one way to find the inverse of a matrix pretty efficiently. So let's do it. Let's say we want to reduce this entry to a 0. So we want to do row 2 minus 2 row 1. Then this will turn into a 2. And then we do the operation on both sides. We get a negative 2 here. Now we want this 2 to be a 0, so we want to do row 1 minus row 2. And then on the side we'll get negative 1. And this entry will change. It'll become a 3. 1 minus negative 2 gives you 3. And then we just want to make this a 1, so we just need to divide the second row by 2. So we just need to do 1/2 row 2. So the left-hand side is now the identity matrix. That means that this matrix here is A inverse. So we can check that that's the inverse now. We can check our work by taking A and multiplying it by A inverse. So the original matrix A, we do A times A inverse. The original matrix A was 1, 2, 2, 6. We multiply by A inverse. So if we do that operation, we get in the first entry 3 minus 2. And then for the second entry, you get negative 1 plus 1. And then 6 minus 6, negative 2 plus 3. So overall, you get the identity matrix. So it works out. So in summary, basically what we did is we took A, we multiplied both sides by some inverse matrices, or by some elementary matrices. On the left, E21, E12, and then like E22. We multiplied these on the left of A, and we ended up with the identity matrix. And so if we multiply, well, this product is A inverse. So the inverse of A is just the product of these elementary matrices. So a fact is that every invertible matrix can be written as a product of elementary matrices. I'll just say is a product of elementary matrices. Basically, that's Gauss-Jordan elimination. And together with that, that means all invertible matrices can be reduced to the identity matrix. So that's one way to identify if a matrix is invertible or not. Every invertible matrix can be reduced to the identity matrix I. So, for example, the matrix 1, 2, 2, 4 is not invertible because the second row is just 2 times the first row. So if you tried to reduce that matrix to the identity matrix by like reducing this entry to 0, you would do row 2 minus 2 row 1, but then you would end up with a 0, 0 at the bottom. So it can't be the identity matrix. Can't be reduced to the identity matrix. Another example would be like 1, 1, 1, 1 for the same reason. Basically, if you have a matrix whose rows are a multiple of another row, or a linear combination of another row, then the matrix can't be invertible. Should I do like a 3x3 example of Gauss-Jordan elimination? Is that a good idea? Okay. So a larger example would be.
Like last time, you never talked about the Gauss-Jordan.
You didn't talk about it?
Yeah. This is dumb.
But did he talk about inverse matrices?
Yeah.
Okay. So if they ask how to find an inverse matrix, or if they say find the inverse matrix of this matrix or whatever, then this is a pretty efficient way of doing it.
This is on week 5 homework, so I think we'll be doing it this week.
Yeah. So first, augment A with the identity matrix. That's 2, 0, negative 1, negative 1. Oh. And then reduce the left-hand side to the identity. Reduce left-hand side to identity matrix. So that means we need to get that to a 0 to start with. So we can do row 2 minus 2, row 1. So 5 minus 4 gives you 1. Get a negative 2 here. Now we want this negative 1 to be a 0. So we'll do row 3 plus row 2. So I can't use the first row here to reduce the third row because then I would pick up a 1 or something in that entry, and we don't want that. So we need to use the second row. So when you do that, you get this matrix, negative 2, 1, 1. Okay, and then we want that to be a 0. Well, at this point, it would actually be more efficient if I reduced this entry first. Because I can do that using row 3. But on the other hand, if I wanted to reduce this upper 2 first. What would happen if I did that? So I would have to do row 1 minus 2 row 2. And so I would end up with 1, 0, negative 4 in that entry.
When you added row 2 to row 3, shouldn't that last entry be 3?
Let's see.
Sorry. Oh, I think I missed an extra sign. Never mind.
Okay, yeah, negative 1 plus 2 gave me 1. Okay. But so yeah, I would get this negative 4 here, and I don't want that. That would give me another entry I have to reduce to 0 in the end. So it's more efficient in this case to get rid of this 2 in red first. So let's do that. I want to do row 2 minus 2 row 3. 0, 1, 0, 0, 0, 1. So negative 2 minus 2 times negative 2 is 2. Then 1 minus 2 is negative 1. Then minus 2. And so the last entry we need to reduce is this 2. And so we just need to use the second row to do that. So now that I have a 0 here, I won't mess anything up by using the second row to reduce the first row. So that's why this was a better way to do it. Row 1 minus 2, row 2. So 1 minus 4 gives you a negative 3. You get a 2 here and a 4 there. And so we've gotten this into identity augmented with A inverse. So that means that this guy is A inverse. That's the inverse matrix. So at this point we could check our work. If we wanted to, we could check that A inverse times A gives you identity matrix, and then you know that you did it right if it works. So that's good for the test, exam, check your work. So we could check that this multiplied by original matrix A gives the identity matrix. So we should check that. Okay, let's do an example of reducing to upper triangular form and doing back substitution. So this is just a method for solving an equation ax equals b, a linear equation system of equations. So let's say we have a matrix A equals -1, 2, 4, 2, -1, -2, -2, 1, 1. and let's say b is this vector 2, 2, 4. We want to solve for the corresponding x such that a times x equals b. And I'll call the components of the vector x by z. Okay, so we want to reduce to upper triangular form, which means we want these entries to be zeros. So first we need to do, well, let's augment A with B first, so that we can keep track of our operations. We want to do, let's say we're reducing this to a 0 first. So we want to do row 2 plus 2 row 1. So that would go to 0. Negative 1 plus 4 would give you a 3 here. Negative 2 plus 8 would give you a 6. And 2 plus 4 gives you 6. So we're there. Now we need that to be a 0. So let's do row 3 plus, or rather minus 2 row 1. So we get a 0 there. 1 minus 4 gives you a negative 3. And then 1 minus 8 gives you a negative 7. And then on the right-hand side, we have 4 minus 4 gives you 0. So that ends up being 0. Now we want this negative 3 to be a 0, so we'll do row 3 plus row 2. So we get that, and some 6s. So it's upper triangular now. That means we can do back substitution to solve for x. So if you write out the system of equations again, it would be negative x plus 2y plus 4z equals 2, 3y plus 6z equals 6, and negative z equals 6. That's the system of equations. So back substitution means solve for z first. So equation 3 says z is negative 6. Then if you take that and use it in the second equation, equation 2 says 3y plus 6 times negative 6 is 6. So 3y is 6 plus 36, which is 42. So y is like 14. So that's y and z. And we can take both of those and use them in the first equation, solve for x. So the first equation said negative x plus 2y, which is 14, plus 4z, which is negative 6, should give you 2. So if we solve for x, 2 minus, let's do 28 plus 28 minus 24 is 4. So negative x is negative 2, which means x is 2. So that's the solution. X equals 2, y equals 14, z equals negative 6. So the vector x is 2, 14, negative 6. That's the answer to the equation AX equals B using upper triangular form and back substitution. What else? What else is there? What else did we do? What other kinds of things were on the homework? So there's some important things about matrix multiplication that we should be aware of. It's associative, so A times B times C is the same as doing A times B times C, so that's nice. It's distributive over addition, so A times B plus C is A times B plus A times C. But notably, it's not commutative, so A times B is not necessarily the same as B times A. So as a consequence of that, you have to be careful when doing things like A plus B squared. We're really used to just writing, if they're real numbers, A squared plus 2AB plus B squared. We're really used to that, but that's not necessarily true for matrix multiplication, because in reality what it is when you distribute this is A squared plus AB plus BA plus B squared. But AB is not the same as BA, so you can't combine them. So it's not necessarily the same. Same thing with like A plus B times A minus B. It's not necessarily the same as A squared minus B squared. So they're going to try to trick you with that. Talk about inverse matrices. Some things about inverse matrices. The product of inverse matrices is also invertible. Invertible matrices, sorry. Product of invertible matrices is also invertible. So if you take two invertible matrices, A and B, and you multiply them together, you can find the inverse of that, and it's B inverse times A inverse. So when you take the inverse of a product of two matrices, you have to swap the order. Because when you wake up in the morning, you put your socks on, you put your shoes on after that. But then when you get home, you got to take your shoes off first, and then your socks. You don't take your socks off and then your shoes. That doesn't make any sense. Same thing with inverse matrices. Well, let's say you have two singular matrices. What about a product of singular matrices? Is that going to be necessarily singular? Like if you take some matrix that doesn't have an inverse, like 1, 1, 2, 2. You multiply it by another matrix that doesn't have an inverse, like I don't know, say one, 1, 1, 1. Neither of those have inverses, but if you multiply them together, let's see, you would get 2 in that entry, 2 in that entry, and then 4 and 4. Well, that's not invertible, so looks like it works out. The product of two singular matrices is not singular. Okay. Let's see, what if you take, okay, what if you add two invertible matrices? If you take two invertible matrices, A and B, and you add them together, is that necessarily going to be invertible? Both these are invertible. Like, what is the inverse of A plus B? Is there a formula for that? Well, if A is like this matrix 1, 0, 0, 0, and B is the matrix 0, 0, 0, you know what, they're supposed to be invertible, right?
Yeah.
So let's take one. Let's take A to be the identity matrix. That's definitely invertible. Let's take B to be negative identity matrix. Okay, those are invertible, but when you add them together, obviously you get the 0 matrix, which is definitely not invertible. Because 0 times anything is just going to give you 0. So the sum of two invertible matrices is not necessarily invertible. Also, what I was doing mistakenly just before, if A and B are singular, their sum is not necessarily singular. So, like what I was writing before, if A is this matrix, which is singular, B is this matrix, which is singular, if you add them together, you get the identity matrix, which is definitely invertible. So, two singular things, add them together, they can be invertible to sum. You guys talk about permutation matrices in class? No. No permutation, no transpose of a matrix.
They just take a look at number 4 in homework.
What was that?
This they asked about to explain something number 4.
Uh-huh.
They get the matrix B is 1, 2, 0, and the second row is 0, 0, 0.
Uh-huh.
So they ask like for any 4 by 3 matrix A, what is the column 3 of 3B?
Uh-huh.
Like those kind of questions they ask.
Right, yeah, so if you take two matrices and you want to find a particular row or column or entry of their product,
It's kind of like that. So they just gave us one matrix, and they said that for any other matrix, they like find this row.
I see.
We also talked about determinants.
Oh, determinants.
Yeah.
Like the determinant of a 2 by 2 matrix.
Yeah.
Yeah, so that's interesting. So the determinant of a 2 by 2 matrix is going to be AD minus BC, right? You just multiply that by that and then subtract the off diagonal. And so there's a formula for the inverse of a matrix using the determinant. The inverse of A. So if A is A, B, C, D, then the determinant of A. Sorry. The formula for A inverse for a 2 by 2 matrix is 1 over the determinant of A. And then swap these and negate these. That's a formula for determinant for the inverse of a matrix using this determinant thing. So that one's nice to know. As for determining, yeah, so this is the problem, right? What is a column 3 of AB? What is a row 2? Yeah, so for example, if you take some matrix A and you take some matrix B, and it's, let's say the columns are B1, B2, B3, those are the columns. Let's say A is M by N, B is N by P, just so we can do the product. So then the columns of A times B are going to be AB1, AB2, AB3. So that's another way to think about the product of two matrices. That might be helpful. Row 2 of BC. DB equals identities. So the part C and D are basically asking about left and right inverses of a matrix. So for a square matrix, if your matrix has, so let's say you have a square matrix A, if you can find a matrix D so that D times A is the identity matrix, then this implies that A is invertible. So you can also do the other side of A. A times D would also be identity matrix. So if you know you have a matrix that's definitely not invertible, then you can't find a matrix that when you multiply it on the left or the right gives you the identity matrix. If you know that your matrix, if your square matrix is definitely not invertible, you can't do that. So one last thing would be, I guess, you take a matrix. Anyone know an example where you take two matrices, you multiply them together, you get 0? These are non-zero. Can that happen? Yeah, probably. That probably works. You can probably do that. Matrices are weird.
So when you say a matrix is non-zero, do you mean none of the values are 0, or they're not all zeros?
Not all 0.
Not all zeros.
Yes.
So just one has to be non-zero.
Right. At least one has to be non-zero. Well, I guess, so earlier we did this kind of thing. Yeah, so if you take a matrix, has a row of zeros, you multiply it by something else, the row of zeros is going to get carried over in that row. So in this case, we have a row of zeros on the top and a row of zeros on the bottom, so they're going to carry over to the product. You're going to have a 0 matrix, but these guys are not 0. So that would be a nice example, but there's a bunch you could do. Any other questions? Hope you found that useful.
Are we having a review next week?
Yes, there will be an exam review on Saturday.
It's 3 o'clock, right?
On this week?
Yes, Saturday, 3 o'clock. I think it's 3 to 5. I don't think it's in here. think it'll be an actual,
C 1.102.
probably an actual classroom, yeah. I'll send an email before that happens with all of the information, because your exam is soon.
Will we cover things we've done in class or things that will be on the exam?
Are there things that you covered in class that are not on the exam?
Yeah, this email they sent earlier today was that the exam covers through section 2.4, which is,
Oh, because we're on 2.5 right now.
yeah.
Then yeah, it'll just be about what's on the exam. Try to keep it to that stuff.